Let's take a look at the Unit 4.3 review. The first question asks you to describe the distillation process and what is it useful for. So I wrote, it's a process where molecules are separated based on their boiling points. If you have a mixture of liquids, you start heating them, and the ones that have the lowest boiling point start to boil first. You can collect their gas vapor and force it through a cooler area so it will condense back into a liquid. When we did this in class, the ethanol had the lowest boiling point, around 78 degrees Celsius, so it started boiling first and it came out into our first beaker and we called it fraction number 1. And then the second highest boiling point for us was water, because water has stronger intermolecular forces holding those molecules together. And last but not least was the glycerin, which actually stayed inside the flask. We never heated up the flask high enough to reach the boiling point of glycerin. The intermolecular forces are very strong. So I also wrote the process is useful for separating any mixture of liquids, but in class specifically we talked about how we separated crude oil into different parts. Question 2. Which of the following molecules would have a higher boiling point and why? It would be the one with the OH, because this molecule is polar. It has strong intermolecular forces because the oxygen is greedier, pulling electrons toward itself, so it will have a partial negative charge and it will attract a partial positive hydrogen nearby. I just saw that there's a typo here. It will attract a partially positive hydrogen of a nearby molecule. This molecule, ethane, only has weak intermolecular forces, dispersion forces holding them together because it's nonpolar. So it would be much easier to break those forces and reach the boiling point, which is where the energy overcomes the attraction of those molecules. How much energy would be required to turn ethanol from a liquid to a gas? Well, we want to locate ethanol's heat of vaporization. And this happens at 351 Kelvin, which the problem also has, so we're right on track. So first thing we're going to have to do is start by writing how much we've got. We've got 100 grams of C2H5OH. We want to get that into moles because this is how much energy it takes to boil 1 mole of ethanol molecules. So if we have 100 grams of ethanol, how many moles do we have? Well, first we have to figure out how much does 1 mole weigh. I added it up using the periodic table and it weighs 46.07 grams. I added up 2 carbons, a total of 6 hydrogens, and 1 oxygen. If I stop and plug that into my calculator now, I get 2.17 moles. It takes 43.5 kilojoules to change 1 mole of ethanol into a gas. So what if we have 2.17 moles? We've got to multiply. This comes out to be 94.4 kilojoules of energy required. What about if we've got liquid acetone and we want to freeze it? Well, let's take a look at acetone. Freezing point is minus 95, so that's right on, and the heat of fusion is 5.72. So once again, though, we're going to start by writing what we know. We've got 75.0 grams of acetone, CH3CO, CH3. Next step, divide by the molar mass. So I've got to add up, let's see, a total of 3 carbons and 6 hydrogens and 1 oxygen. That added to 58.08 grams. I'm going to stop there, and that is 1.29 moles. Multiply by the value in the table for the heat of fusion, how much energy it takes to freeze, or how much energy is released to freeze 1 mole, and we have a little over 1 mole, 1.29 7.29 moles. So that comes out to be 7.39 kilojoules of energy released. From the following graph, it says determine the melting, freezing, boiling, and condensation points. Well, the melting and freezing points are the same, and that would happen at -20, because that's when the first plateau is. And the boiling and condensation point would be at the +20. And remember, boiling and condensation are also the same, because they're just opposite directions, going from a liquid to a gas, or from a gas back to a liquid.